Okay, we need to introduce one more piece of mathematical background here. That's a generalization of Taylor series. So you've talked about Taylor series in one dimension, and what we're going to do here is we're going to talk about this now in multiple dimensions. So a multivariate Taylor series looks like that expression at the top of the slide. Now it looks scary because it's got gradients. It's got a gradient in it, and it's got a Hessian in it there. But if you think about the gradient being a first derivative and the Hessian being a second derivative, then the form of this is exactly the same. You know, that's a u squared. That's a second derivative of f times u squared divided by 2. That's a term that looks exactly like the squared term in a one-dimensional Taylor series, and that's the a gradient of f term times u. That's exactly the same as the sort of term as you have in a one-dimensional Taylor series. You also have a remainder expression here. So at the second order, so if you expand a function f of x plus u, some vector u, as using the linear term in a Taylor series, which is that. There's a remainder term that's got a squared term in it, so that's my u squared, the u transpose with the u. There's like the u squared in a 1D Taylor series with a second derivative of f that's evaluated at some uncertain, some unknown value z here. And the only difference is that that z sits somewhere between x and u. So this is the form of this exactly maps to a one-dimensional Taylor series. I'm just using the scary-looking multivariate calculus terms and things in here. So let's try and explain where this expression comes from. So I'm going to attack this by looking at a particular function here. It's a function of t. So g of t, which I'm going to write down as f of x plus tu. So if I give you an x and a u, a vector x and a vector u, if they're fixed, then this is really a function of just of t, right? And so we'll call that g of t. That's a new one variable function of t. And the idea of this f, if I take it as a function of a vector here, so x plus tu, which I'll call y, then that means it's a function of x1 plus tu1, so the first element of that, the second element of that, the third element of that, etc., etc., etc. Now, what I need to do here is if I'm going to figure out what all these gradient terms here are here, right? If I need to figure out these, all these different derivative terms, so if I think about writing down a Taylor series of this thing, then I need to differentiate. So g prime of t, what does that mean? Well, that means the derivative with respect to t of this object here. Right? So I'm differentiating this function f with respect to t. Now, to differentiate this with respect to t, I have a function of a function, because really, I have f of y here, and y is a function of t. Right, so the point here is that I need to use the chain rule on this expression. If I'm going to differentiate f of y, right, let's even write that. Let's maybe even write that in here. Right, then I'm differentiating with respect to y and then with respect to t. And that's the classic case where we have to use the chain rule. So how do we use the chain rule? So you might remember that in one dimension, df dt, well, df dt was df dy, so I'm just scribbling this down in one dimension, now off to the side. The chain rule in one dimension looks like this. The derivative of df dt, if f is a function of y and y is a function of t, would be df dy dy dt. And so that's the that's what I'm going to use here. I just have this in multiple dimensions. So I need the multi-dimensional chain rule. Now, in multiple dimensions, the chain rule looks a little bit different. I'll write it a bit larger here. df dt. Now I need to be careful with my notation. So I have this same form, df dy dy dt. I just have lots of different y's now. I've got y1, y2, all the way up to yn. Right, and so we get these all the way through dt plus dot 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 dot. Right, so the multivariate chain rule looks like that. So I've written partial derivatives because there are multiple different y's. Differentiating f with respect to y is a partial derivative, but each of these y's is a function only of t, so they get d's, regular d's. They are normal ordinary derivatives. So okay, so let's look at this. Let's look at this object here. Now, if I differentiate f with respect to y1, right? Or in other words, with respect to the first component here, well, I get df1. I'll write it as df dy1 for starters, and then dy1 dt. So if I differentiate this with respect to t, I'm just going to get a u1. Right? So I'll write this. You could write this like that, and then I could keep summing along here. There's a slightly better notation. This y, I don't really love having to introduce this y here. So I'm going to write a shorthand for this bit. So I'm going to write this. I'm going to write that partial derivative, so the derivative of f1 with respect to its first component there. So that subscript 1 is going to mean a shorthand for the partial derivative of f with respect to its first component. And then the u1 comes about from differentiating this first component, x1 plus t u1, with respect to t. I'm getting a u1. All right, so if I do that, then I'll keep getting this same pattern all the way up to the nth term here, xn plus t un. And so we get that as we differentiate along and along. Okay, now what does that object look like? So I've got the gradient of f with respect to its first component, second component, third component, all the way up to nth component. And then I've got another term that looks like u1, u2, the vector u, all the components of the vector u. And then I've got those things multiplied together and summed up. So that looks like a dot product, right? A shorthand way of writing this would be to take f, calculate its gradient, and then you get, and then you can write that like that. So that's the first derivative, g prime. G prime of t is that. So I need to do all the other derivatives here as well. So let's do the second derivative, so g prime prime t. If I differentiate that again, well, I'm going to get this same deal coming through here. So I'm going to have to differentiate this object here with respect to t. So I'm going to get d by dt of this giant object here, which I'll write like u1 f1 x1 plus t u1 plus u2 f2 x2 plus t u2. Right, so that's just directly differentiating that, and I flipped around these two because it will look nicer in a sec. Okay, so if I'm doing the derivative of that sum, I should be able to flip the sum and the u's here, right? So there are no t's inside this, these u's, so I should be able to pull the derivative inside and just do the derivative of these. So I've got a sum here. I should be able to sum from I equals 1 up to n. And then I can write this as I've always got ui. I can pull the derivative inside, and I've got the derivative, just the d by dt, of all of these f terms. So fi xi plus t ui. Yes. Right. So that's just pulling the derivative inside. So pulling the derivative inside, the derivative only needs to operate on the f's, and then compactifying this into a summation notation. And now once I've got that, so now the derivative of all of these f's, well, I mean, that's the original problem that I did, right? So the derivative of f gives me a thing that looks like this, gives me a sum that looks like that, right? Or in other words, you know, exactly this thing that I started off with here. So differentiating this again, I'm going to use the multivariate chain rule again, right? And I'm going to end up with another sum here, another sum of ui's times fi's. So I'll get another sum, right? So I'll get a sum from I equals 1 to n. I'll also get a new sum coming in from j equals 1 to n. I'm going to get my ui's, and then I'm actually going to get some new uj's coming in here, right? So I'm going to get this sum returned again, and now I'm going to get the derivatives of all of these f terms with respect to each component, the first, second, third, etc. component again. So I'm going to get the derivative of all my fi's with respect to every j now. So that uj has come about by the chain rule, just as it came about up here. It comes about again when I differentiate again, and so I get this ui times uj, and then I'm summing all of these up. And now I've got, this is representing, I'm taking the derivative with respect to the ith component, and then the derivative with respect to the jth component of this internal thing. And, you know, I've got the sum of all of these things. Maybe I'll write this for those who like, who know about this sort of notation. Actually, I should cut these, make these vectors sort of a better way to do this. I'll put the uj's at the end so that I get ui times fij times uj. And then for people who know about the, who like that notation, can then recognise that if I expand this, or if I contract this back to vector notation, then I'm going to get, you know, I've got derivative with respect to the ith component, derivative with respect to the jth component. That is the Hessian of f. X plus tu times the vector u. So I get that term there. So that's the second derivative, and I could keep going here. All right. Now that I've done that, let's let's think about the Taylor series. You know, what am I doing here? I started off with this function g of t. Right, so if I calculate the Taylor series for this 1D function g of t about t equals 0, then that's going to look like this. So g of t equals, so forget everything, just think about the Taylor series of a function. That will look like t g prime of naught plus t squared over 2 g double prime. Right. And now if I think, now I know what g prime of 0 is, right, if I plug in t equals 0 into this, I'm just going to get, I'll get g of 0 here plus t u transpose u transpose gradient of f of x plus t squared on 2 and then that g double prime, which is this. Etc., etc., etc. So we get this expression coming out here, and of course I can when these disappear. I think. So the Taylor series. So come back to my picture here. Hopefully, what you should be able to do is identify each of the terms in this expression. With these derivatives. So, that's a long-winded way of showing you that the multivariate Taylor series is exactly the same, and in fact, it comes from the 1D Taylor series. It's just you have to, you're basically using the multivariate chain rule instead of just differentiating things simply. So we won't talk about how the remainder theorem comes out, but it sort of maps, if you wanted to map it through, it comes out in exactly the same way. Now, why did this? There's one thing that I've missed here. Why did these t's disappear? I need one more line here at t equals 1. This is why. So g of 1 here is, that represents, g of 1 represents f of x plus u. And these things, and then I just get g of naught, which is f of x. Right, that's 1, and now these things are exactly the same. So this should be actually t plus u. That makes more sense. So these things are correct. So if I plug in f of x, and now that maps. And now that maps exactly. Essentially all this is, all this ugly formula is using the multivariate chain rule to come up with these derivatives and then plugging into the 1D Taylor series for this function g of t. And that's how you derive it. What do you need to take away from this? You need to take away this formula. You need to take away the fact that it maps exactly, that the reason that we have a gradient term here, which is like a first derivative, is not accidental, and the reason that we have a Hessian term here, which is like a second derivative, and a u transpose and a u, which is like a u squared, is not accidental as well. And these things map exactly onto the 1D Taylor theorem. That's all.